Hello there, and welcome back to the Midnight Sleep Scientist. I'm so glad you've returned for another cosmic journey. Tonight, we're setting our sights on our nearest galactic neighbour, Andromeda, a magnificent spiral of light floating in the darkness, 2.5 million light-years away, yet slowly drawing closer with each passing moment. You've got nothing to do but rest. Let your shoulders drop, your breathing deepen, and your mind wander among the trillion stars of this ancient galaxy. Because tonight we aren't simply observing from afar, we're exploring the vast spiral arms, the dense galactic core, and the invisible dark matter halo of a galaxy larger and older than our own. A cosmic island that holds secrets about galactic evolution, stellar archaeology, and the future merger that will reshape both our galaxies forever. From its supermassive black hole to its extended stellar streams, from blue supergiants burning bright to ancient red dwarfs that have glowed for billions of years, Andromeda tells the story of how galaxies grow, collide, and begin anew. Some of what you hear tonight may surprise you, or at the very least spark some quiet curiosity as you drift towards sleep. And just before we begin, if these gentle cosmic explorations help you unwind, or give you a peaceful way to end your day, consider liking and subscribing to the channel. It helps other stargazers find their way here too, one sleepy soul at a time. Now let's begin our journey to Andromeda. Andromeda is racing toward us at 250,000 miles per hour. Though it lies over 2.5 million light-years away, Andromeda is moving in our direction faster than most bullets leave a gun barrel. This sounds dramatic, but cosmic distances are so vast that the galaxy's approach is gentle by astronomical standards. Each year, it draws about 2,000 miles closer, a distance you could drive in a day, yet negligible across the void between galaxies. The approach has been steady for billions of years. Gravity's patient pull drawing two spiral islands together across the dark. Andromeda is the most distant object visible to the naked eye. On a clear moonless night, far from city lights, you can spot Andromeda as a faint, oval smudge in the constellation of the same name. That dim glow contains the light of 1 trillion stars, each one a sun in its own right. When you look at Andromeda, you're seeing the galaxy as it was 2.5 million years ago, its ancient light having travelled across the void while humans were just beginning to walk upright on Earth. It's a direct connection to deep time, visible without any instrument except your eyes. The galaxy spans 6 times the width of the full moon, though Andromeda appears as a small fuzzy patch to the naked eye. Its full extent covers an enormous area of sky. If our eyes could see its faint outer regions, the galaxy would appear 6 times wider than the full moon. Most of the structure is too dim to see without sensitive instruments, but it's there, a vast halo of ancient stars and dark matter stretching far beyond the bright central regions. Andromeda is not just a distant point of light, it's a massive cosmic structure that subtly dominates a large section of our night sky. Andromeda contains over 1 trillion stars. While our Milky Way hosts an estimated 100 to 400 billion stars, Andromeda dwarfs our galaxy with more than 1 trillion stellar inhabitants. These range from massive blue supergiants burning through their fuel in just millions of years, to tiny red dwarfs that will shine for hundreds of billions of years. The sheer scale defies imagination. More stars in Andromeda alone than there are trees on Earth, grains of sand on all our beaches, or seconds that have passed since our planet formed. The galaxy is twice the width of the Milky Way, measuring approximately 20,000 light-years across. Andromeda significantly outspans our home galaxy's 100,000 light-year diameter. Its spiral arms sweep through space in graceful curves, each one containing billions of stars, vast molecular clouds, and active star-forming regions. If you could see both galaxies from the side, Andromeda would appear as the larger sibling, its disk more extended, its mass more substantial, its gravitational influence reaching farther into the cosmic deep. Ancient light carries the story of stellar generations. The starlight streaming from Andromeda carries information encoded across billions of years. Blue regions mark where young, hot stars illuminate stellar nurseries with ultraviolet radiation. Yellow and red areas reveal older stellar populations, the accumulated glow of countless sun-like stars that have aged gracefully over cosmic time. By analyzing this light, astronomers can read the galaxy's history, when bursts of star formation occurred, how heavy elements were distributed, and how the galaxy's structure evolved across the eons. Andromeda rotates in a complex dance. Unlike a solid wheel, different parts of Andromeda rotate at different speeds. The inner regions complete their circuits more quickly, while the outer spiral arms lag behind in a more leisurely rotation. This differential rotation shapes the spiral structure itself, winding the arms tighter over time and creating density waves that trigger new episodes of star formation. The galaxy doesn't spin as one piece. It flows like a cosmic river, each stellar stream following its own gravitational current. The galaxy's core blazes with the light of billions of suns. At Andromeda's heart lies a dense nuclear bulge packed with ancient red and yellow stars. This central concentration contains much of the galaxy's stellar mass compressed into a relatively small space. The core is so bright that it outshines many entire galaxies, a beacon of accumulated starlight that has been building for over 10 billion years. Within this radiant center lurks a supermassive black hole, invisible but revealed by the rapid orbital motion of nearby stars. Two satellite galaxies dance around Andromeda. The galaxy doesn't travel alone through space. Two smaller elliptical companions, designated M32 and M110, orbit Andromeda in a gravitational embrace that has lasted for billions of years. These satellite galaxies are themselves composed of billions of stars, yet they appear as mere smudges next to their giant companion. Like moons around a planet, they follow elliptical paths through Andromeda's extended dark matter halo, slowly spiraling inward as gravitational friction robs them of orbital energy. Andromeda's spiral arms tell a story of cosmic recycling. The galaxy's elegant spiral structure is painted by ongoing cycles of stellar birth and death. Massive stars are born in the dense spiral arms, burn brilliantly for just a few million years, then explode as supernovae, enriching the interstellar medium with heavy elements. These enriched clouds then collapse to form new generations of stars, creating an ongoing cycle of cosmic renewal. The spiral arms are not permanent features but dynamic patterns that persist as matter flows through them over hundreds of millions of years. Andromeda formed through cosmic collisions and mergers. Like most large galaxies, Andromeda built itself through a process of hierarchical assembly, growing larger by consuming smaller neighbors over billions of years. Its smooth outer halo contains streams and shells of stars, the disrupted remains of dwarf galaxies that wandered too close and were gravitationally shredded. Each merger added mass and angular momentum, gradually building the magnificent spiral we observe today. Andromeda is not a pristine creation, but a composite structure, stitched together from the ruins of cosmic collisions across deep time. The galaxy's dark matter halo extends far beyond the visible stars. Like all large galaxies, Andromeda is embedded within a massive halo of dark matter, mysterious particles that outweigh the visible stars by at least 5 to 1. This invisible scaffolding extends hundreds of thousands of light years beyond the bright spiral disk, its gravitational pull holding the galaxy together and shaping the orbits of satellite galaxies. Without dark matter, Andromeda's outer regions would fly apart, unable to maintain their rapid rotation against the weak gravitational pull of distant stars. Ancient globular clusters orbit in the galactic halo. Scattered throughout Andromeda's extended halo are several hundred globular clusters, dense, spherical collections of ancient stars that formed when the galaxy was young. These stellar time capsules contain some of the oldest stars in the local universe, their composition revealing the chemical conditions that existed over 12 billion years ago. They orbit the galactic center on highly elliptical paths that carry them far above and below the main disk, like a swarm of stellar satellites following the galaxy's deeper gravitational rhythms. The central supermassive black hole weighs 100 million times more than our Sun. At Andromeda's heart lurks one of the most massive black holes in the local universe, a gravitational monster containing the mass of 100 million suns compressed into a region smaller than our solar system. This cosmic heavyweight influences the motion of stars across thousands of light years, its presence revealed by the high-speed orbits of nearby stellar populations. Though currently dormant, this black hole likely powered brilliant quasar activity billions of years ago when the galaxy was younger and more gas-rich. Star formation peaked billions of years ago. Andromeda's most vigorous period of star formation occurred roughly 2 to 5 billion years after the Big Bang, when the galaxy was rich in pristine gas and dust. During these cosmic construction years, new stars formed at rates many times higher than today's more sedate pace. The galaxy consumed much of its available fuel during this period, building the massive stellar populations we observe today. Modern star formation continues, but at a gentler rate, as much of the remaining gas has been heated or dispersed by billions of years of stellar evolution. The galaxy shows evidence of past interactions. Andromeda's structure bears subtle scars from gravitational encounters with smaller companions. Its outer disk is warped and asymmetric, likely shaped by tidal interactions with satellite galaxies or passing dark matter concentrations. Streams of stars extend far into the surrounding halo, the disrupted remains of smaller galaxies that were torn apart by Andromeda's gravitational field. These fossil signatures reveal a dynamic past filled with cosmic collisions and close encounters that continues to shape the galaxy's evolution. Stellar streams trace ancient mergers wrapped around Andromeda like ghostly ribbons. Are numerous stellar streams, long, thin structures composed of stars stripped from disrupted satellite galaxies. These streams are the smoking guns of past mergers, each one representing a smaller galaxy that was captured and dismembered by Andromeda's superior gravitational pull. The streams follow specific orbital patterns that allow astronomers to reconstruct the merger history and understand how the galaxy assembled itself over cosmic time. The nuclear disk harbors complex stellar populations. Within Andromeda's central regions lies a massive disk of stars oriented differently from the main galactic plane. This nuclear disk contains distinct stellar populations with different ages, metallicities, and orbital characteristics. The structure likely formed through a series of minor mergers that deposited material into the galactic core, creating a complex architectural record of the galaxy's assembly history. It's a library of stellar archaeology, written in the orbital patterns of billions of ancient suns. In 4.5 billion years, Andromeda will merge with the Milky Way. Gravity's inexorable pull ensures that our two galaxies are destined for a cosmic collision that will fundamentally reshape both spiral structures. Computer simulations predict that the encounter will begin with long-range gravitational disturbances that stretch and warp both galaxies before the final coalescence. The merger will be a slow-motion ballet played out over hundreds of millions of years, ultimately producing a single larger elliptical galaxy that astronomers have already nicknamed Milkameda. The collision will be surprisingly gentle for individual stars. Despite the dramatic nature of the galactic merger, direct stellar collisions will be extremely rare due to the vast spaces between stars. The average distance between stars in a galaxy is like grapes separated by hundreds of miles. Even when two galaxies interpenetrate, their stellar populations mostly pass by each other harmlessly. However, gravitational interactions will fling many stars into new orbits, some escaping the merged system entirely to wander alone through intergalactic space. Both galaxies will lose their spiral structure. The elegant spiral arms that currently define both the Milky Way and Andromeda will be destroyed during the merger process. Gravitational tides will stretch and twist these structures beyond recognition, mixing their stellar populations and dispersing their organized patterns. The final merged galaxy will likely resemble a giant elliptical, a smooth, featureless ball of stars lacking the spiral structure that characterizes younger, more gas-rich systems. Beauty of a different kind will emerge from the chaos. The collision may trigger massive star formation. When the gas-rich regions of both galaxies collide and compress, they may trigger intense bursts of new star formation, a phenomenon astronomers call a starburst event. These episodes can form stars at rates hundreds of times faster than normal, quickly consuming available gas supplies while illuminating the merging system with brilliant young stars. The collision will breathe new life into both galaxies, at least temporarily, before the available fuel is exhausted and star formation subsides to lower levels. Our solar system will likely survive intact. While the galactic merger will dramatically alter the large-scale structure around us, our solar system should remain gravitationally bound and relatively undisturbed. The Sun and planets orbit so closely together compared to galactic scales that they form a stable, compact unit, unlikely to be disrupted by the gravitational chaos occurring around them. We may find ourselves in a very different part of the merged galaxy, perhaps flung into the outer halo, or settled into the new elliptical structure, but the Earth-Sun system should persist. The merged galaxy will be larger but less active. Milkameda will contain the combined mass of both parent galaxies, making it one of the largest members of the local group. However, the violent merger process will heat and disperse much of the remaining gas, reducing the fuel available for future star formation. The merged system will be a mature, evolved galaxy populated mainly by long-lived red dwarf stars with little new stellar birth to replace the massive stars that burn out quickly. It will be a quieter, more sedate cosmic environment. Andromeda hosts different generations of stars with distinct histories. The galaxy's stellar content reads like a cosmic family tree, with different populations revealing distinct chapters in its evolutionary history. The oldest stars, formed over 12 billion years ago, populate the central bulge and outer halo. With their reddish metal-poor light, intermediate-age populations dominate the disk, while the younger stars, blue giants and brilliant supernovae, mark active star-forming regions in the spiral arms. Each generation carries chemical fingerprints that reveal the conditions under which they formed. The galaxy's metallicity varies with location and age. In astronomy, metals refer to all elements heavier than helium, forged in stellar cores and distributed through supernova explosions. Andromeda shows clear metallicity gradients. The central regions are enriched with heavy elements from billions of years of stellar evolution, while the outer disk and halo contain more primitive metal-poor stars. This chemical archaeology allows astronomers to trace how heavy elements were gradually distributed throughout the galaxy over cosmic time. Red dwarf stars will outlive the galaxy itself. The most numerous stellar inhabitants of Andromeda are red dwarf stars, small, cool suns that burn their hydrogen fuel so efficiently they can shine for hundreds of billions of years. These stellar tortoises will continue glowing long after larger stars have exhausted themselves, eventually becoming the last lights in an aging galaxy. Their extreme longevity means that red dwarfs forming today will still be shining when the universe is many times its current age, the final stellar embers in a cosmos growing dark and cold. Blue supergiant stars create cosmic fireworks. At the opposite extreme are massive blue supergiants, stars dozens of times more massive than our Sun, that burn brilliantly but briefly. These stellar candles illuminate Andromeda's spiral arms with intense ultraviolet radiation, ionizing surrounding gas clouds and triggering shock waves that can initiate new waves of star formation. Their lives are violent and short, ending in spectacular supernova explosions that can briefly outshine billions of normal stars while enriching the interstellar medium with heavy elements forged in their cores. Binary star systems dominate the stellar census. Most stars in Andromeda don't live alone, but exist in binary or multiple star systems where two or more stars orbit their common center of mass. These stellar partnerships can persist for billions of years, but they also create some of the most exotic and violent phenomena in the galaxy. When one star in a close binary system evolves into a white dwarf or neutron star, it can strip matter from its companion, leading to nova explosions, X-ray emission, or even the complete disruption of both stars. White dwarf stars mark stellar graveyards. Scattered throughout Andromeda are roughly 100 billion white dwarf stars, the hot, dense cores left behind when sun-like stars exhaust their nuclear fuel. These stellar remnants are incredibly dense, packing roughly the mass of our Sun into an object the size of Earth. They cool slowly over billions of years, gradually fading from white-hot to red to invisible brown dwarfs. White dwarfs represent the ultimate fate awaiting the vast majority of stars, including our own Sun in about 5 billion years. Variable stars serve as cosmic lighthouses. Andromeda contains millions of variable stars whose brightness changes over regular periods due to pulsations in their outer layers. Sepinfied variables are particularly valuable. Their pulsation periods directly relate to their intrinsic brightness, making them excellent distance indicators. By measuring sepinfides in Andromeda, astronomers first established that spiral nebulae were actually separate galaxies far beyond our Milky Way. These stellar lighthouses continue to serve as crucial tools for measuring cosmic distances and galaxy evolution. Dark matter shapes Andromeda's invisible skeleton. Though we see Andromeda as a beautiful spiral of stars and gas, most of the galaxy's mass exists in an invisible form called dark matter. This mysterious substance doesn't emit, absorb, or reflect light, revealing itself only through gravitational effects on visible matter. Andromeda's dark matter halo extends several times farther than its visible stars, providing the gravitational scaffolding that holds the galaxy together and shapes the motion of everything within it. The galaxy's rotation curve defies expectations. According to Newtonian physics, stars farther from Andromeda's center should orbit more slowly, just as outer planets move more leisurely around the Sun. Instead, stars in Andromeda's outer regions orbit almost as fast as those near the center, a pattern that can only be explained by the gravitational influence of dark matter. This flat rotation curve was one of the first convincing pieces of evidence for dark matter's existence, and remains one of its strongest observational signatures. Invisible streams connect Andromeda to its neighbors. Computer simulations predict that Andromeda is connected to nearby galaxies by thin streams of dark matter called cosmic filaments. Magnetic fields thread through the galactic disk. Like the Milky Way, Andromeda possesses a large-scale magnetic field that threads through its spiral structure. This invisible field influences the motion of charged particles, shapes the flow of ionized gas, and affects how cosmic rays propagate through the galaxy. The magnetic field aligns with the spiral arms and may play a role in triggering star formation by helping compress gas clouds to the densities needed for gravitational collapse. The galaxy sits within a vast cosmic void. Andromeda, the Milky Way, and other local group galaxies exist within a region of space that is unusually empty compared to the cosmic average. Andromeda's influence extends far beyond its visible boundaries. The galaxy's gravitational reach extends several times farther than its visible stars, encompassing a vast spherical region called the galactic halo. Within this extended zone, numerous satellite galaxies orbit like cosmic moths around a brilliant flame. The halo also contains globular clusters, stellar streams from disrupted galaxies, and vast quantities of hot, ionized gas that emits X-rays detectable by space telescopes. Hot gas fills the space between galaxies. The region around Andromeda isn't empty, but filled with extremely hot, thin gas heated to millions of degrees. This galactic corona is so diffuse that it contains fewer atoms per cubic centimeter than the best vacuum achievable on Earth. Yet its total mass may rival that of the visible stars. The hot gas provides a record of past galactic activity, supernova explosions and stellar winds that heated and ejected material from the galactic disk into the surrounding halo. Ancient stellar populations preserve galactic archaeology. The halo stars surrounding Andromeda are among the oldest in the universe, formed when the galaxy was young and the cosmos contained fewer heavy elements. These stellar fossils preserve information about conditions in the early universe, the galaxy's initial formation, and the first episodes of star formation. Their chemical composition serve as cosmic DNA, revealing family relationships between different stellar populations and the merger history that assembled the modern galaxy. Hypervelocity stars escape into intergalactic space. Occasionally, gravitational interactions near Andromeda's central black hole or close encounters between binary star systems can accelerate individual stars to velocities exceeding the galaxy's escape speed. These hypervelocity stars are flung out of the galaxy entirely, destined to wander alone through the intergalactic void. They represent a small but steady loss of stellar mass as the galaxy gradually leaks its contents into the surrounding dark. The galaxy's corona connects to the cosmic web. Andromeda's hot gas halo doesn't exist in isolation, but connects to the larger scale structure of the universe through filaments of warm, hot intergalactic medium. These tenuous bridges channel matter between galaxies and may provide the fuel for continued, albeit slow, galactic growth. The connections are so diffuse they're difficult to detect directly, but computer simulations predict they should exist and play important roles in galactic evolution. Heavy elements were forged in stellar cores across billions of years. Every atom heavier than hydrogen and helium in Andromeda's stars, planets, and interstellar medium was created through nuclear fusion in stellar cores or explosive nuclear synthesis during supernova events. The galaxy has been running this cosmic alchemy experiment for over 10 billion years, gradually enriching its gas supply with carbon, oxygen, silicon, iron, and dozens of other elements essential for planet formation and potentially life itself. Supernova explosions distribute metals throughout the galaxy. When massive stars reach the end of their lives, they explode as supernova with energies that can briefly outshine entire galaxies. These catastrophic events scatter the heavy elements forged in stellar cores across vast distances, mixing them with the interstellar medium where they become incorporated into new generations of stars and planets. Without supernova, the universe would contain only hydrogen and helium, making rocky planets and life as we know it impossible. The galaxy's chemical evolution varies by location. Different regions of Andromeda show distinct patterns of chemical enrichment that reveal their star formation histories. The central bulge, rich in old stars that formed rapidly early in the galaxy's history, shows high abundances of alpha elements like oxygen and magnesium, produced by short-lived massive stars. The disk regions show more gradual enrichment patterns reflecting billions of years of continued star formation and chemical evolution. Stellar winds sculpt bubbles in the interstellar medium. Even stars that don't explode as supernovae influence their surroundings through powerful stellar winds, streams of charged particles flowing outward at speeds of thousands of kilometers per second. These winds carve out vast bubbles and cavities in the interstellar gas, creating complex structures visible in radio and infrared observations. The combined effect of stellar winds from many stars helps regulate star formation by dispersing dense gas clouds. Planetary nebulae return processed material to space. When sun-like stars exhaust their nuclear fuel, they gently puff off their outer layers, creating beautiful planetary nebulae, glowing shells of ionized gas surrounding hot white dwarf cores. These elegant death shrouds return chemically enriched material to the interstellar medium, contributing to the gradual increase in heavy element abundances over cosmic time. Planetary nebulae represent a gentler form of stellar recycling compared to violent supernova explosions. Andromeda's spiral arms are density waves moving through the stellar disk. The galaxy's elegant spiral structure isn't composed of fixed groups of stars, but represents patterns of enhanced density that rotate more slowly than individual stars. As stars orbit the galactic center, they periodically move into and out of these spiral density waves, spending more time in the arms where traffic becomes congested. This compression triggers star formation, illuminating the spiral pattern with young, bright stars before they drift back into the interarm regions. Gas flows create complex patterns throughout the disk. The interstellar medium in Andromeda's disk doesn't sit still, but flows in complex patterns driven by stellar winds, supernova explosions, gravitational perturbations, and magnetic forces. Large-scale gas motions include spiral shockwaves that compress molecular clouds, galactic fountains that carry material above and below the disk plane, and turbulent cascades that mix enriched material throughout the interstellar medium. Star-forming regions trace the spiral pattern. The most active star formation in Andromeda occurs in dense molecular clouds compressed by passage through spiral density waves. These stellar nurseries are marked by bright emission nebulae, regions where ultraviolet light from hot young stars ionizes surrounding hydrogen gas, causing it to glow with characteristic red light. The spiral arms are outlined by these glowing star-birth regions, creating the galaxy's distinctive appearance in photographs. Molecular clouds serve as stellar nurseries. Scattered throughout Andromeda's disk are thousands of giant molecular clouds, cold, dense regions where hydrogen exists in molecular form and temperatures drop to just a few degrees above absolute zero. These clouds can span hundreds of light years and contain enough material to form millions of stars. When gravitational instabilities or external compression triggers collapse, these molecular clouds fragment into dense cores that eventually ignite as new stars. The galaxy's disk shows signs of past disturbances. Andromeda's disk isn't perfectly smooth, but shows warps, asymmetries, and other structural irregularities that reveal its dynamic history. These features may result from gravitational interactions with satellite galaxies, past merger events, or encounters with dark matter concentrations. The disk's current structure represents a snapshot of ongoing gravitational sculpting that has been shaping the galaxy for billions of years. M32 orbits close to Andromeda's core, one of Andromeda's two prominent satellite galaxies. M32 is a compact elliptical system located unusually close to its giant companion. This proximity has stripped away much of M32's outer stellar halo, leaving behind a dense central core that orbits Andromeda every few 100 million years. The satellite's stripped material may have contributed to some of the stellar streams visible in Andromeda's halo, representing ongoing galactic cannibalism on a cosmic scale. M1110 follows a more distant orbit. The second major satellite, M110, maintains a more comfortable distance from Andromeda and retains more of its original structure. This elliptical dwarf galaxy contains several billion stars and shows evidence of recent star formation, unusual for elliptical systems. M110's orbit carries it through Andromeda's extended halo on a path that will eventually bring it closer to the central galaxy, where tidal forces will begin stripping away its stellar content. Dozens of smaller satellites populate the outer halo. Beyond the two prominent companions lie numerous smaller dwarf galaxies bound to Andromeda by gravity. These faint systems contain anywhere from millions to billions of stars and represent some of the least massive galaxies known. Many are so dim they've only been discovered in recent surveys, suggesting that the complete census of Andromeda's satellite population remains incomplete. The satellite system shows signs of past disruptions. Many of Andromeda's satellite galaxies show distorted shapes, extended stellar distributions, or other signs of gravitational harassment by their massive companion. Some satellites have been completely disrupted, their stars scattered into the thin stellar streams that wrap around Andromeda's halo. The satellite population represents an ongoing feast, as the giant galaxy gradually consumes its smaller neighbors. Satellite orbits reveal dark matter distribution. The orbital motions of Andromeda's satellites provide crucial information about the distribution of dark matter in the galaxy's extended halo. By tracking how these small galaxies move under Andromeda's gravitational influence, astronomers can map the invisible mass that dominates the system. The satellite orbits suggest that dark matter extends far beyond the visible stars, comprising the majority of the total galactic mass. Ancient stars preserve records of cosmic dawn. The oldest stars in Andromeda formed when the universe was less than 1/5 its current age, preserving in their atmospheres the chemical signatures of that primordial epoch. These stellar fossils contain almost no elements heavier than helium, reflecting the pristine conditions that existed before generations of massive stars had time to forge and distribute heavy elements through supernova explosions. They serve as direct probes of the universe's youth. Chemical abundance patterns reveal star formation history. Different elements are produced through different nuclear processes and dispersed on different timescales, creating distinctive chemical signatures that evolve as galaxies age. By measuring the abundances of various elements in stars of different ages, astronomers can reconstruct how star formation proceeded in different parts of Andromeda over cosmic time, identifying periods of intense activity, quiescent phases, and the influence of major merger events. Globular clusters serve as fossil records. The several hundred globular clusters orbiting in Andromeda's halo represent some of the galaxy's oldest stellar systems, formed during intense episodes of star formation in the galaxy's youth. Each cluster contains hundreds of thousands of stars that formed simultaneously from the same gas cloud, providing snapshots of conditions at specific moments in galactic history. The age and chemical composition differences between clusters reveal multiple formation epochs. Stellar streams trace ancient mergers. The ghostly streams of stars wrapped around Andromeda are the disrupted remains of smaller galaxies consumed over billions of years. Each stream follows a specific orbital pattern that allows astronomers to reconstruct the merger event that created it, when the smaller galaxy was captured, how massive it was, and what path it followed during its final death spiral. These streams serve as archaeological evidence for the hierarchical assembly process that built modern galaxies. White dwarf cooling ages date stellar populations. White dwarf stars, the remnants of sun-like stars, cool predictably over billions of years, providing cosmic clocks that can date different stellar populations. The coolest white dwarfs in Andromeda's halo are among the oldest objects in the galaxy, formed when the universe was young and the galaxy was just beginning to take shape. Their temperatures reveal ages approaching the age of the universe itself. Andromeda will exhaust its star-forming fuel. Like most large galaxies, Andromeda is gradually converting its gas supply into stars while losing additional material through stellar winds and supernova explosions. Computer models predict that the galaxy will consume most of its remaining star-forming fuel over the next several billion years, transitioning from a gas-rich spiral to a gas-poor elliptical system. The most active phase of Andromeda's evolution is already behind it. Red dwarf stars will dominate the far future. As star formation slows and massive stars burn out, Andromeda's stellar population will become increasingly dominated by long-lived red dwarf stars. These small, efficient nuclear furnaces can burn for hundreds of billions of years, far longer than the current age of the universe. In the distant future, red dwarfs will be the last stars shining in an aging galaxy, providing the only remaining sources of light and energy. The galaxy's structure will continue evolving. Even after the merger with the Milky Way, the combined system will continue evolving through stellar evolution, dynamical relaxation, and interactions with other galaxies in the local group. Over tens of billions of years, the merged galaxy may grow through additional minor mergers while gradually losing mass through stellar evolution and the evaporation of weakly bound stars from its outer regions. Stellar evolution will reshape the galaxy's appearance. As massive blue stars burn out and sun-like stars evolve into red giants, Andromeda's appearance will gradually shift toward redder colors dominated by long-lived, low-mass stars. Dark energy will eventually isolate the local group. On the larger scales, the accelerating expansion of space driven by dark energy will gradually separate galaxy clusters and eventually isolated galaxy groups like our own. In the far future, Andromeda, the Milky Way, and their merged descendant will find themselves increasingly alone in an expanding universe where other galaxies have receded beyond the cosmic horizon. The local group will become its own isolated island universe. Distance creates observational difficulties. While Andromeda is our nearest major galactic neighbor, Its 2.5 million light-year distance makes detailed studies challenging. Individual stars can only be resolved in the galaxy's outer regions using the largest ground-based telescopes, while the crowded central regions require space-based observations to separate individual stellar sources. Much of our detailed knowledge comes from studying the integrated light of stellar populations rather than individual stars. Dust lanes obscure parts of the galaxy. Like most spiral galaxies, Andromeda contains significant amounts of interstellar dust that absorbs and scatters light, particularly at shorter wavelengths. These dust lanes create dark patches visible in optical images and can hide star-forming regions and other interesting structures. Astronomers use infrared observations to peer through the dust and reveal the hidden architecture of the galaxy's spiral arms and central regions. The galaxy's large angular size complicates observations, spanning more than 3 degrees on the sky, 6 times the width of the full moon. Andromeda is too large to be captured in a single field of view by most telescopes. Comprehensive studies require mosaics of many separate observations stitched together, a time-consuming process that limits the detail possible in any single survey. The galaxy's size is both a blessing and a curse for astronomical observations. Stellar crowding limits resolution in central regions. The dense concentration of stars in Andromeda's central bulge creates severe crowding that makes it difficult to study individual stellar sources or measure precise motions. Even the Hubble Space Telescope struggles to separate individual stars in the densest regions, where millions of stellar points of light blend together into a smooth glow. This crowding effect makes it challenging to study the detailed properties of stellar populations in the galaxy's core. Redshift measurements reveal galactic motion. Despite its approach toward us, Andromeda shows a slight overall redshift due to the expansion of the universe. However, different parts of the galaxy show different Doppler shifts. One side is slightly more redshifted as it rotates away from us, while the other side is blue-shifted as it approaches. These velocity measurements allow astronomers to map the galaxy's rotation pattern and measure its total mass through gravitational dynamics. The local group shapes galactic evolution. Andromeda doesn't exist in isolation, but as part of a gravitationally bound collection of galaxies called the local group. This cosmic neighborhood includes the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. Gravitational interactions within this group influence each member's evolution, triggering star formation, stripping away gas, and ultimately determining the timing of future mergers. Intergalactic gas connects neighboring systems. The space between local group galaxies isn't empty, but filled with extremely thin, hot gas that may have been expelled from the galaxies themselves through stellar winds and supernova explosions. This intergalactic medium serves as a reservoir that could potentially fuel future star formation if conditions allow the gas to cool and condense back into galaxy disks. The cosmic web influences galactic properties. On larger scales, the local group sits within the cosmic web, a vast network of dark matter filaments that connect galaxy clusters across the universe. Matter flowing along these filaments may have influenced the formation and evolution of local group galaxies, channeling gas inflows and affecting the timing of major merger events throughout cosmic history. Void environments affect galaxy evolution. The local group resides in a region of below-average galaxy density, which may have allowed its members to evolve in relative isolation compared to galaxies in denser environments. This cosmic solitude permitted the survival of extended gas disks and ongoing star formation that might have been disrupted by more frequent galaxy interactions in crowded cluster environments. X-ray binaries mark stellar graveyards. Throughout Andromeda's disk and halo, astronomers have identified numerous X-ray sources marking the locations of exotic stellar remnants, neutron stars and black holes accreting matter from companion stars. As material spirals onto these dense objects, it heats to millions of degrees and emits intense X radiation. These systems represent the final stages of stellar evolution, where ordinary stars have collapsed into some of the most extreme objects in the universe. Supernova remnants expand through interstellar space. The aftermath of stellar explosions can be seen throughout Andromeda as expanding shells of hot gas glowing in radio and X-ray wavelengths. These supernova remnants continue expanding for thousands of years after the initial explosion, sweeping up surrounding interstellar material and creating bubbles in the galactic medium. They serve as stirring spoons that mix heavy elements throughout the galaxy, while triggering new waves of star formation through compression of nearby gas clouds. Planetary nebulae create cosmic art. Scattered throughout the galaxy are thousands of planetary nebulae, beautiful shells of glowing gas, expelled by dying sun-like stars. These objects create some of the most aesthetically striking astronomical phenomena, with complex shapes sculpted by stellar winds, magnetic fields, and binary interactions. Each planetary nebula represents the gentle death of a star similar to our Sun, returning processed material to the interstellar medium for future generations of stars and planets. Pulsars spin with clockwork precision. Among Andromeda's stellar population are pulsars, rapidly rotating neutron stars that sweep beams of radio emission across space like cosmic lighthouses. These objects rotate hundreds of times per second with timing precision that rivals atomic clocks. Pulsars represent one of the most extreme states of matter in the universe, with magnetic fields trillions of times stronger than Earth's and surface gravity so intense that a sugar cube-sized piece would weigh as much as a mountain. Hypervelocity stars escape the galaxy. Occasionally, gravitational interactions near massive black holes or three-body encounters in dense stellar environments can accelerate stars to velocities exceeding Andromeda's escape speed. These hypervelocity stars are ejected from the galaxy entirely, destined to wander alone through intergalactic space. They represent a slow leak of stellar mass, as the galaxy gradually loses some of its contents to the cosmic void. Metallicity gradients reveal galactic assembly. The abundance of heavy elements in Andromeda's stars varies systematically, with distance from the galactic center. Inner regions show higher metallicities built up through billions of years of stellar evolution in the dense central environment, while outer regions retain more primitive compositions reflecting less efficient mixing and star formation. These metallicity gradients provide crucial clues about how the galaxy assembled and how chemical enrichment proceeded over cosmic time. Stellar nucleosynthesis creates the periodic table. Every element heavier than hydrogen and helium found in Andromeda was forged in stellar cores through nuclear fusion, or created during explosive stellar death throes. Different stellar masses produce different elements through distinct nuclear processes. Massive stars create elements up to iron through fusion, while even heavier elements require the extreme conditions found in neutron star mergers or core collapse supernovae. Alpha element enhancement reveals rapid star formation. Certain stellar populations in Andromeda show enhanced abundances of alpha elements like oxygen, neon, and magnesium relative to iron. This pattern indicates periods of rapid star formation, when massive stars, which produce alpha elements, exploded as supernovae before intermediate mass stars had time to contribute iron through Type 1a supernovae. The pattern serves as a chronometer, revealing the timescales of ancient star formation episodes. Cosmic ray acceleration enriches the interstellar medium. Supernova shockwaves accelerate charged particles to enormous energies, creating cosmic rays that permeate the galaxy. These high-energy particles contribute to the chemical evolution of the interstellar medium through spallation reactions that create light elements like lithium, beryllium, and boron. Cosmic rays also influence the dynamics of interstellar gas by providing additional pressure support against gravitational collapse. The galactic nucleus harbors complex stellar dynamics. Within the central few thousand light-years of Andromeda lies a complex stellar system with multiple components, a classical bulge dominated by old stars, a younger stellar disk, and possibly a bar structure that channels gas toward the central black hole. The nuclear region contains a significant fraction of the galaxy's total stellar mass concentrated into a relatively small volume, creating a unique environment with stellar densities thousands of times higher than our solar neighborhood. Past activity left its mark on the core. Evidence suggests that Andromeda's central black hole was much more active in the past, possibly powering a brilliant quasar that would have made the galaxy visible across much of the observable universe. The signatures of this ancient activity may still be detectable in the form of large-scale outflows, unusual stellar populations, or structures in the surrounding hot gas. The galaxy's quiet present belies a more violent pattern. Dense star clusters orbit the central black hole. The immediate vicinity of Andromeda's supermassive black hole contains several dense star clusters whose orbits are shaped by the black hole's intense gravitational field. Stars in these clusters experience extreme tidal forces and high encounter rates that can disrupt planetary systems and alter stellar evolution through collisions and close encounters. These central regions represent some of the most extreme stellar environments in the galaxy. Nuclear star formation may be triggered by bar-driven inflows. If Andromeda possesses a central bar structure, it could channel gas from the outer disk toward the nuclear regions, potentially triggering episodes of star formation in the galactic center. This process occurs in many barred galaxies, and may explain some of the younger stellar populations observed in Andromeda's nucleus. The bar acts as a gravitational funnel, concentrating the galaxy's fuel in its core. Large-scale magnetic fields thread the galactic disk. Like most spiral galaxies, Andromeda possesses organized magnetic fields that follow the spiral arm pattern and extend far above and below the main stellar disk. These fields influence the motion of charged particles, affect how cosmic rays propagate through the galaxy, and may play important roles in regulating star formation by providing additional pressure support in molecular clouds. Turbulent motions stir the interstellar medium. The space between stars and Andromeda is filled with turbulent gas motions driven by stellar winds, supernova explosions, and gravitational instabilities. This turbulence prevents the interstellar medium from settling into a smooth, static distribution, and instead maintains a complex, ever-changing structure of filaments, bubbles, and density fluctuations that influence where and when new stars form. Magnetic reconnection powers high-energy phenomena. In regions where magnetic field lines of opposite polarity come together, they can suddenly reconnect and release enormous amounts of stored magnetic energy. These reconnection events may contribute to heating the hot gas in Andromeda's halo, accelerating cosmic rays, and driving outflows of material from the galactic disk into the surrounding medium. Dynamo processes maintain galactic magnetism. The organized magnetic fields observed in Andromeda must be continuously regenerated since they would otherwise decay due to turbulent motions in the interstellar medium. The galaxy likely operates as a large-scale dynamo, using the combined effects of rotation and convective motions to stretch and amplify weak seed magnetic fields into the strong, organized structures we observe today. Tidal streams reveal ongoing galactic cannibalism. Wrapping around Andromeda in long, thin arcs are stellar streams, the disrupted remains of satellite galaxies and star clusters that ventured too close to the massive galaxy's gravitational field. These streams follow specific orbital patterns that allow astronomers to reconstruct the properties of the original objects and understand how Andromeda has grown through accretion over billions of years. The giant stellar stream extends across the halo. One of the most prominent substructures in Andromeda's halo is a giant stellar stream that wraps around the galaxy for hundreds of thousands of light-years. This stream likely originated from a dwarf galaxy, with a mass similar to the small Magellanic Cloud that was completely disrupted by tidal forces several billion years ago. Its stars now follow nearly identical orbits around Andromeda, creating a ghostly river of light in the outer halo. Shell structures mark ancient mergers. In addition to streams, Andromeda's halo contains shell-like structures, curved concentrations of stars that formed when smaller galaxies were completely disrupted during merger events. These shells represent material that was scattered during the collision and has since settled into stable orbital patterns. Each shell corresponds to stars that have completed similar numbers of orbits since the merger event that created them. Substructure reveals the galaxy's dark matter distribution. The detailed shapes and kinematics of stellar streams and shells provide unique probes of Andromeda's dark matter halo. Since these structures are sensitive to the overall gravitational potential, their properties can reveal how dark matter is distributed throughout the galaxy's extended halo. This information is crucial for understanding galaxy formation and the nature of dark matter itself. The local group environment influences evolution. Andromeda's evolution has been shaped by its membership in the local group, where gravitational interactions with the Milky Way and other neighbors affect its structure and star formation history. These environmental effects become more important as the galaxies approach each other, with tidal forces already beginning to influence the outer regions of both spiral galaxies. Cosmic ray pressure affects galactic dynamics. High-energy particles, accelerated by supernova shocks and other violent events, create cosmic ray pressure that can influence the dynamics of interstellar gas. In some regions of Andromeda, cosmic ray pressure may be comparable to thermal and magnetic pressures, affecting how gas flows through the galaxy and where star formation occurs. The galaxy's motion through the cosmic web. Andromeda moves through space at several hundred kilometers per second relative to the cosmic microwave background, indicating motion through the larger scale structure of the universe. This motion may affect how the galaxy interacts with the intergalactic medium, and could influence the accretion of fresh gas from the cosmic web. Ram pressure from intergalactic gas. As Andromeda moves through the thin intergalactic medium, it may experience ram pressure that can strip gas from its outer regions and affect star formation in the disk. While this effect is much weaker than in dense galaxy cluster environments, it may still play a subtle role in the galaxy's evolution over cosmic time. Next-generation telescopes will revolutionize Andromeda studies. Upcoming observatories like the James Webb Space Telescope, the Extremely Large Telescope, and the Roman Space Telescope will dramatically improve our ability to study individual stars, star formation regions, and other structures in Andromeda. These instruments will allow astronomers to resolve stellar populations with unprecedented detail and study the galaxy's chemical evolution, stellar archaeology, and dark matter distribution with much greater precision. Gravitational wave astronomy opens new windows. The detection of gravitational waves from merging black holes and neutron stars provides a new way to study extreme phenomena in nearby galaxies. Future gravitational wave observatories may be sensitive enough to detect mergers occurring in Andromeda, providing insights into the galaxy's population of compact objects and the physics of strong gravitational fields. Multi-messenger astronomy combines different signals. By combining information from electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays, astronomers can gain more complete pictures of energetic processes in Andromeda. This multi-messenger approach is particularly powerful for studying transient events like supernovae, gamma-ray bursts, and tidal disruption events around massive black holes. Andromeda represents cosmic perspective. Contemplating our neighboring galaxy provides profound perspective on humanity's place in the universe. The galaxy contains 1 trillion stars, each potentially hosting planetary systems, yet appears as a faint smudge to the naked eye. This juxtaposition between the vast and the intimate invites reflection on scales of space and time that dwarf human experience, while simultaneously connecting us to the broader cosmic story. The merger symbolizes cosmic impermanence. The inevitable collision between Andromeda and the Milky Way reminds us that even the largest structures in the universe are temporary. Galaxies form, evolve, merge, and eventually fade away as their stars burn out and the universe expands and cools. This cosmic impermanence provides perspective on the transient nature of all structures, from galaxies to civilizations. Looking at Andromeda is looking into the past. When we observe Andromeda, we see the galaxy as it existed 2.5 million years ago, before modern humans had evolved on Earth. The light we see tonight has been traveling through space since our earliest ancestors walked the African savanna. We are directly observing ancient history preserved in starlight, connecting present moment awareness with deep cosmic time. The galaxy challenges our imagination. Andromeda's trillion stars, vast distances, and billion-year timescales stretch human comprehension beyond its everyday limits. Contemplating such scales can be both humbling and inspiring, revealing the limitations of our intuitive understanding, while opening our minds to the magnificent complexity and beauty of the cosmic environment we inhabit. We are made of stellar material. Every atom in our bodies heavier than hydrogen was forged in the core of a star, similar to those now shining in Andromeda. We are literally made of star stuff. The calcium in our bones, the iron in our blood, the oxygen we breathe all originated in stellar furnaces. Billions of years ago, looking at Andromeda, we see not just a distant galaxy, but the cosmic foundry that created the very elements of our existence. As we conclude our gentle drift through Andromeda's cosmic architecture, let these trillion stars remind you of the vast beauty that surrounds us in space. You have wandered through spiral arms painted with stellar nurseries, gazed into the dense galactic core, where a supermassive black hole shapes the motion of billions of suns, and traced the ghostly streams of ancient mergers that built this magnificent galaxy over cosmic time. Tonight, as your breathing slows and your thoughts grow quiet, remember that you are connected to this distant galaxy through the fundamental elements that compose your body. The iron in your blood was forged in stellar cores similar to those burning throughout Andromeda's disk. The calcium in your bones was scattered by supernovae whose light once illuminated cosmic gas clouds in our neighboring galaxy. You are not separate from these distant stars, but intimately connected to them through billions of years of cosmic evolution. While you rest, Andromeda continues its slow approach toward our Milky Way, drawing 2,000 miles closer each year in a cosmic dance that will culminate in merger billions of years from now. The galaxy's trillion stars burn quietly in the darkness, some being born in stellar nurseries, others dying in brilliant supernovae, all participating in the ongoing cycles of stellar evolution that have shaped the cosmos for over 13 billion years. In this quiet moment before sleep, you exist at the intersection of the vast and the intimate, a conscious observer in a universe of trillion-star galaxies, temporary collections of stellar matter that have somehow organized themselves into the capacity for wonder. You are both infinitesimally small in the cosmic scale and miraculously significant as a pattern of matter and energy capable of contemplating the very cosmos from which you emerged. The ancient light from Andromeda continues streaming toward Earth tonight, carrying information about stellar births and deaths, chemical evolution, and galactic dynamics across 2.5 million years of travel through intergalactic space. Some of those photons may reach your eyes as you glimpse the galaxy's faint glow in tomorrow's night sky, connecting your present moment of consciousness with the deep cosmic past. Sleep well in the knowledge that you drift not through empty space but through a universe rich with galaxies, alive with stellar fire, and pregnant with possibilities we have only begun to imagine. You are a temporary arrangement of ancient stellar material that has somehow awakened to contemplate its own cosmic origins. In your dreams tonight, may you find peace in that extraordinary improbability. Rest now, fellow traveller. The stars will continue their ancient burning while you sleep, and Andromeda will continue its patient approach across the cosmic deep. The universe is vast beyond comprehension, yet here you are within it, conscious, curious, and connected to everything you have imagined tonight, through the invisible threads of physical law and cosmic history.